So can you see my screen?
Yes, ma'am.
Okay. And the recording has also started because no one is.
Yeah, I started that.
It started. Okay. So far, you all have done a lot of discussions on the form of the wave function and the approximation and the symmetries that it should have. And our first approximation is the single determinant for the wave function, that is the Slater determinant. And today we will focus on a complementary aspect, that is the Hamiltonian. And we will hopefully cover two things. We will talk about how the Hamiltonian is written in atomic units and also how to evaluate the matrix elements of the Hamiltonian for single determinants. And the rules for doing this are called Slaters rules. Okay, so all this follows very closely Zhao and Ostlund. So if you get your hand on a PDF of this book, you will be totally fine for, I think, almost 95% of this course. Okay. So the first thing we will talk about is the atomic units and how to write the Hamiltonian in atomic units. So, okay. So this is the first time I'm doing a live class on an iPad, so I will be a bit slow. So pardon me. Okay. So the Hamiltonian is written. So this is the many electron Hamiltonian, and we have this. Okay, so let's see. I will just write it for the hydrogen atom. So that helps me write fewer terms. Okay. So then I can delete the sum I. It is only one electron. And I can also delete this. And I only have one nucleus electron interaction term. That is E squared by R. Okay. And R I can write as, you'll see why I'm writing it in a less convenient manner very soon. So this is R. And of course, del squared is equal to del squared, del x squared, del y squared plus del squared, del z squared. Okay. Now, what I want to do is, of course, to remove the units from x, y, and z. So I don't want x, y, z to be centimeters or meters or anything. So what you do is you scale x, y, z with a factor lambda. Okay, and we shift the units from x, y, z to lambda. Fine. And in doing so, my Hamiltonian then becomes, oh, sorry, I missed a minus here. So minus h cross squared by 2me. I will get a lambda squared out over here. And I will get a del prime squared, let's say. Okay. And a 1 by 4 pi epsilon 0. A lambda will come out over here. And I have an e squared by, I'll just write this now as r prime since I've shown the scaling. Okay. Fine. And now that we have this, we impose a further condition to find out the value of lambda, which will actually be my conversion factor from, let's say, SI units to atomic units. And the atomic units will be such that my operators will be unit free. Okay, so here basically x, y, z, x prime, y prime, and z prime These are dimensionless. Fine. And then what I want to do is I want to condition for lambda. So let's say I simply want to remove all these constants uh, from my operator. Okay, and that is the condition by which I will determine the conversion factor lambda. So then I say that h cross square by 2me 1 by lambda square is equal to minus 1 by 4 pi epsilon 0 e square by lambda, and this is and this has the unit of energy, as you can probably guess, because the other side of the Schrodinger equation is energy into wave function, and this is h into wave function. So these have a unit of energy. So I will denote this constant by something that looks like an energy, so epsilon, and I call this a conversion factor to atomic units for energy. Okay. Well, at this point, of course, we don't know that this is exactly the conversion factor of the energy from SI units to atomic units, but we can call this some constant. I'm just using this notation to make it clear later on. Okay, so this is there, and then I compare these two, and I can find out lambda. So then lambda turns out to be 4 pi epsilon 0 h cross square by e square me. Now, why have I not included the 2? So that we have not included the 2 because we want to keep the 2 in our dimensionless Hamiltonian. Okay. So what we want our Hamiltonian to be is minus half del square minus 1 by r. So this is what we want. Okay, so this is a convention. This is how it was done historically, and it also helps in identifying lambda as a constant, which is the Bohr radius. Now, can anyone tell me how we identify this so easily as the Bohr radius? Anyone? So what is the condition that you use for a hydrogen atom to obtain the Bohr radius? Do you remember? Like, what is the derivation?
The angular momentum on that orbit has to be like integral multiple of h cut. All those.
Yes, that is one condition, and the other one, that is part of the derivation, and the other part is,
Coulomb,
Force balance.
yeah, and the other part is the force balance. Yes. So when you use the Coulomb force equal to the centripetal force and the quantization of angular momentum, you end up with this expression for the with this. Okay, you cannot see my pen, right? So you end up with this expression for the Bohr's radius, and here. Uh, As a byproduct of wanting our Hamiltonian to be dimensionless, we see that the conversion factor for lengths from SI to atomic unit is the Bohr's radius. So SI to atomic units, AU, for lengths is the Bohr radius. Okay. And the energy that you obtain by putting lambda equal to A0 is the conversion factor for the energy. So this is the so SI to atomic unit for energy. That is EA. So then when we put back EA into the original Hamiltonian, so that is H is equal to, then I get Uh, well, this one is, I should not have taken the negative sign here. I guess that you don't mind that, right? So this is fine. So then this turns out to be minus epsilon A, and I get what sorry, a plus epsilon A, and then I get this inside the Hamiltonian. Fine. And now I write the Schrodinger equation as
Can you repeat, madam?
yeah. So I've just written the Hamiltonian. So what I did, I had made a mistake here. I had used the negative sign in this equation for lambda over here, but now I just erased the negative signs. So that keeps my negative sign in the Hamiltonian. Okay. Okay, so this 2 I deleted later on. Okay. Hmm. So then in my Hamiltonian, I can take EA as common, and I have minus half grad square minus 1 by r prime. So this I get from here. So yeah. So over here, if I put epsilon A or EA, whatever you like to call it, then I have EA in both the terms, and I can take that common, and I get the Hamiltonian in the dimensionless form that I want. Okay. And now I write this scaled Schrodinger equation. And because I'm writing a scaled Schrodinger equation, I'm writing the wave function with a prime. So so in the wave function also you have x prime, y prime, and z prime. Okay. And this is the energy, and again phi prime. Fine. And now I can write the h with epsilon a, okay, minus half okay. Then I take epsilon a to the other side. Okay. And now this is my energy in atomic units, and this is what is called a Hartree. So this is just the name of the unit that you use. The atomic unit of energy is Hartree. Okay. Then this is now H. Let's say H. No, I will not confuse things. Okay. Let's just put it like this. And now everything is in a primed quantity. So I can remove the primes and say that my Schrodinger equation, dimensionless Schrodinger equation, is simply minus half del square minus 1 by r, some wave function phi is equal to E phi. This is my dimensionless Schrodinger equation, or you can say it is a Schrodinger equation in atomic units. Okay, so what this helps in doing is it helps us from that it has the advantage that you avoid carrying along all these constants like epsilon 0, h cross, me. These are very small values, and numerically they are a problem because they're so small. And it also helps in scaling the energy by a certain number that makes even the energies of the states more reasonable in terms of numerics. So that is why you will see that in quantum chemistry, the Schrodinger equation is always written in this dimensionless or atomic unit form. Okay. So I wanted to just show you that what the criteria is for doing these atomic units. Okay. Now, in addition to the atomic units for energy and length, which come out of this analysis, what you get, there are atomic units for other things as well. So, atomic units for other quantities, they have been chosen to be as follows. So, the charge of the electron is considered to be 1. H cross is considered to be 1, Me is considered to be 1, and 4 pi epsilon 0 is also considered to be 1. And these are consistent with the criteria we have used to determine the conversion factor for length, which is this one. Okay. And there are atomic units for other things as well. Let's say you can have atomic units for magnetic fields, electric fields, and other things as well. Okay. But for now, it is enough for us to look at the energy and the length scale here, and notice that all the constants from the Schrodinger equation are gone. Okay, so that was about the atomic units. Yeah, anything more? No, that is all about the atomic units. We will next talk about how to obtain the okay, no, I want to say something more about the Hamiltonian actually. So the Hamiltonian we have written for the hydrogen atom over here. That is just the kinetic energy of the electrons and the nuclear electron attraction. However, there are other interactions which we have left out of the Hamiltonian. So then what Hamiltonian is this? This Hamiltonian is what is called the non-relativistic field-free Hamiltonian. So it is non-relativistic because here you have you don't have any speed of light over here. That is one thing that you will have in a relativistic Hamiltonian. You will also have you cannot represent it with spin orbitals, a wave function, a relativistic wave function. Okay, and you will also have more terms which involve electromagnetic quantities like let's say, what is an easy example? So like the interaction of the nuclear spin with electrons via currents, etc. So those things are not present in the non-relativistic Hamiltonian, and field free in the sense of there not being any external field. So if there was an external, let's say an electric field, you would have a term with the electric field. If you had an external magnetic field, you would have multiple terms with the magnetic field. So all that is absent from this Hamiltonian, and we already struggle with solving this, so we will not go into more difficult Hamiltonians. Okay. So this is the Hamiltonian that we will talk about throughout this course. Maybe later on we can discuss a few additional terms that could come into the Hamiltonian. Okay. And now we will try and compute the matrix elements of the Hamiltonian. So this is the next part, which is the matrix elements of the Hamiltonian. So as you have done before, if we have a 2-electron system, then the then the wave function can be written as a Slater determinant of 2 spin orbitals. So I have chi1 x1, chi1 x2. I hope this is what is the notation in Zabu-Ostlund. then chi2x1, chi2x2. Okay. So, mm, yeah, I think that is the notation. Yes, that is the notation in Zabo-Osman. Fine. And you have a normalization factor, which is 1 by root 2 for a 2 electron case. Right? And this is the, let's say this is the wave function for the ground state, psi 0. So what do we want to do? So what we want to do is we want to evaluate the matrix element of psi 0, h psi 0. And we want to express it in terms of integrals over spin orbitals. Fine. So what we want to do is we want to analytically simplify this expectation value to integrals over spin orbitals, and then these integrals over spin orbitals can be evaluated numerically. Now, evaluating matrix elements of determinants is numerically, as well as even if you try to do it by hand, quite cumbersome. But we'll see that there are certain very simple simplifications which help us to reduce it to simple evaluations, and this is what is called Slaters rules. Okay, we will do the 2 electron case and generalize it for the n electron case. Okay, Zabo-Osman also shows the general derivation for the n electron case generally, but then that is a bit complicated and I will not do it in class. If you are interested, you can go through it, but you will not actually require it. What you will need to do is, of course, to be able to apply the Slaters rules to evaluate matrix elements of various operators. Okay. So this is the wave function. I will also explicitly evaluate the wave function and write it down for reference later on. So this is basically chi1 x1, chi2 x2 minus chi2 x1, chi1 x2. This is the wave function if I open out the determinant. So first we do so H, the Hamiltonian, has two parts, a 1 electron part and a 2 electron part. Okay, if I write it in very simply, and then for the 2 electron system, the Hamiltonian can be explicitly written as the 1 electron part of for electron 1, the 1 electron part for electron 2, and the 2 electron part, which involves the separation of electron 1 and 2. R12 is the distance between electron 1 and electron 2 at any point of time. Okay. Now the first things, so is this form of the Hamiltonian clear to you? Do you remember what small h contains? Or should I go through it once more? I believe Professor Pal used this notation of small h. If do you remember? Otherwise, I can repeat it. Just tell me and I'll repeat it. No? Okay. Okay, I will repeat it anyway since I'm not getting a response. I will repeat it anyway. Okay. So the full Hamiltonian, this has a, now I'm talking about the full molecular Hamiltonian, not the electronic part, the full Hamiltonian. That has a nucleus repulsion. Okay. It has a nuclear kinetic energy. It has a nucleus electron attraction. It has an electron-electron repulsion. And anything else? And it has a electron kinetic energy. Okay. Now this is the common part between the electrons and the nucleus. So this is dependent on both the coordinate of the electron and the coordinate of the nuclei. This is only dependent on R. This is only dependent on R. Fine. Now these three terms together, they constitute the electronic Hamiltonian. Okay. This constitutes the nuclear Hamiltonian. This, sorry, these three. Okay, I will define the nuclear Hamiltonian later. It's cumbersome over here. Okay. Yeah, this is the electronic Hamiltonian. And then the equation that we are trying to solve is H electronic psi electronic equal to E electronic psi electronic. And why can we do this? The Born-Oppenheimer approximation, which tells me that the total psi can be written as a product of psi nuclear and psi electronic. Okay. Now, that is that. And then when we calculate the energy of the molecule, then what we include is the nucleus repulsion, because that is an important part of the energy of the full molecule. So then the Born-Oppenheimer approximate energy for the molecule is equal to E electronic that you obtain from the electronic Schrodinger equation plus the nucleus repulsion. Fine. And this is just number that you add to the energy that you obtain by solving the electronic Schrodinger equation. And so now we are focusing on H electronic. And there attraction, nucleus electron attraction, and electron repulsion. These are multiplicative operators. And you have the kinetic energy of the electron, and the operator is grad squared, so that is a differential operator. Fine. And this is what you need to solve the Schrodinger equation. And even inside this, you have, if you think of a 2-electron system now, okay? Now I'm thinking of a 2-electron system. Then my H electronic is simply the kinetic electrons then you have the nucleus electron attraction of the 2 electrons. So R A1. So let's say the molecule is, let's say just an atom with one nucleus A. That simplifies things. And 2 electrons, 1 and 2. Okay. Minus ZE square RA2. And then we have electron, which is 1 by R12. So which electron 1 is this? These two terms depend on R1. These two terms depend on R2. And this depends both on R1 and R2. So then these first four terms are called one electron terms. And combining the two, you get H of 1 plus H of 2 plus 1 by R12. So now is it clear what goes into the small h, what is called the one electron term? Okay. And then this together is called the one body part of the Hamiltonian, and this is called the two body part of the Hamiltonian. So theta 1 and theta 2 operators are basically the sum over all the operators of all the electrons. Okay, and when I write small h, then it depends on which electron. Okay, so you can have a small h for electron 1, a small h for electron 2, etc. And when I say theta 1, then theta 1 is basically sum over all electrons, small hi. Okay. Similarly, theta 2 is a sum over all unique pairs of electrons, 1 by Rij. This can also be written as half sum I and j 1 by Rij. And
Ma'am,
this is called an unrestricted. Yeah, sure.
one question. The first grad 1 square, that is depends on just small r1 and capital R also included. Capital R and also small r1. The Hamiltonian electronic. Why also just small r1?
Oh, this one you mean? This is only the kinetic energy of the electron.
Oh, R and the Z square by capital R A1. That is just small.
Capital R A1. No, this also depends on capital R, but that is a parameter now for the H electronic. Yeah, so if you want, I can also write it depends upon R. But that does not matter now. That is just a number. So this is
Oh,
under the Born-Oppenheimer approximation.
okay.
Yeah. In general, it depends. Yeah, if you want, in general, it does depend. But since here I have also written it as just one nucleus, then there is no capital R actually in this particular case. And also, even if there were like more nuclei, then there could have been a capital R dependence.
Oh, okay, okay.
But that would also be a parameter.
Oh, just
That
small
should
r1
not
electronic
affect.
coordinate. Okay, just
Yeah,
electronic
this is
coordinates.
just the electronic coordinate.
Okay.
And this one, okay. But I will not write the R here. We will get confused later on. Okay. So then, okay. So now we have revised what is there in the one electron part and what is there in the two electron part. Fine. So now we will go back to evaluating matrix elements. So let me write it again. So we want to find out this one. Okay. So then I can split up, and this is okay, electronic. And I will write, so I will not keep writing EL, okay, so now we will continue only with the electronic Hamiltonian. So this is theta 1 plus theta 2 psi 0, okay. And inside this we have one more part. So the first thing is we want to do is psi 0 H 1 psi 0, okay. So what does this look like? So let's write. So now I will I will write a lot of detail. Okay, so I hope, So is my font size for writing okay? You can see all my 1 and 2 and everything. Because
Yes,
I will
ma'am.
write a lot of details now. Yeah, okay. So the integral looks like, so do you remember the form of psi naught now? It was chi1 x1 chi2 x2 minus chi2 x1 chi1 x2. Okay. So this star, then we have the operator h. Okay, when I say 1, that actually means x1, right? So it's hx1. And then we have again the same wave function chi1 x1 chi2 x2 minus x2 x chi2 x1 chi1 x2. Okay, integrated over dx2 dx1 dx2. Okay, so now we inspect it. Let's see. So h depends only on x1. So anything that depends on x2 can be integrated independently. So let's look at the first term from here and the first term from here. Then uh, I I will now write it in Dirac notation, because just to make it smaller. So this is chi1 h chi1. This is this one, and we have chi2 depending on x2 and chi2 depending on x2. Then we have the next term. Sorry. Now I will do, okay, this one and this one. So when I do this one and this one, I have plus chi1 h chi2 and chi2 chi1. Then I have the negative term. The first one is, let's say, this and this. So I have minus chi2 h chi1, and I have chi1 chi2. Okay. And then we have the next one, which is now, I have to think of another symbol. Okay, this one and this one. That is chi1 h chi2 and chi2 chi1. Okay, so now you recall that the spin orbitals are orthonormal, right? So easily, which two, we have two terms which go to 0. So no, sorry, three terms which go to 0. So you have this is 0, this is 0, and this is also 0. Okay, and this is equal to 1. So I have chi1 h1 chi1. Oh no, what happened? I should have had chi2 x2 chi2. Must have made a mistake here. This and this. See, y'all didn't notice. I made a mistake in this term. So this will be chi2 chi1. And then this is 1. So I have chi1 H chi1 plus chi2 H1 chi2. And now let's put the normalization factor. So my determinant had a 1 by root 2. So you have a 1 by root 2 into 1 by root 2, and you would have had a half, right? And there would be a half here. And there is a half here. Okay. So you agree with the derivation?
Yes, ma'am.
Okay. Fine. So this is H1. This is psi 0 H2 psi 0. That is equal to, again,
Are you writing? Hello.
I am writing now the, yeah, hello?
It's not visible, ma'am, here.
Yeah, hello?
It's stuck at one point. I'm saying a screen is stuck at one point. It's not visible. Yeah,
okay.
now it's visible. Yes.
Okay, then let's just wait for a few seconds. Can you see the screen moving now?
Yes, ma'am. Can you repeat from theta
Is
1
moving?
this H1 plus H2?
Theta 1. Okay, okay.
Yes,
So
ma'am.
theta 1 is the sum of the one electron operators of all the electrons. So it's H1 plus H2. So now we have solved the psi naught H1 psi naught. So, and by H2 chi1 plus chi2 H2 chi2. And if we sum these two now, then psi 0 theta 1 psi 0, that is, so the half will go because these are the same, this and this expression. Is it? Is it the same? Do you think they are the same, the two expressions?
They are not the same, ma'am, because Hamiltonian is different.
Yes.
Hamiltonian is
That
different.
is right. Hamiltonian is different, so they are not the same. But I can write this as now a sum. So let's say I keep the half and I write the sum as I H J psi I, and this is sum over I and J. Okay, and is that right? No, that is also not right actually. This has to be So I can write it like this. Then what should we do? Then we should add this and this. Yeah. This is fine. H1, H2. Yeah, this is fine, right? This expression is fine. This expression is fine, but there is one more simplification that we in this integral. In this expression, I can interchange the coordinates of 1 and 2. Can I or can I not? What do you think? In this
Yes,
expression,
because
can
they
I
are dummy
interchange?
indices.
I can only interchange it if I also interchange the left hand side. Isn't it? Or not? Yes or no? This is integrated over coordinates of electron 2. This is integrated over coordinates of electron 2. And so is the left hand side. So if I want to change 1 and 2, I have to also change the left hand side. So I can't do that here. Because the left hand side also depends on the coordinate of electron 2. No? Am I confusing you? Yeah. Okay. I will make it clear. So the thing is that here this is a number. So this is a number. This is also a number. Okay. So this just apparently looks like it depends on the coordinate of electron 2. But the electrons are indistinguishable. So that kind of crops up again here. So the value, so this value is actually the same as the value for electron 1. Because this is a number and 1 and 2 are indistinguishable. So then when I add them, so it becomes, so basically then psi naught H1 psi naught is equal to psi naught H2 psi naught. Okay, because this, it does not matter what I am calling the electron. Because I am integrating over either all of R1 or integrating over all of R2. So, and they give me a number. So they turn out to be the same. Okay, so then it is not, so I can actually simplify this expression even more. And I can write it as, so let me put it in a different color. That psi naught theta 1 psi naught is actually simply sum over I chi I H 1 chi I. I can write it as any A. I mean the H of any electron. It does not matter which
Ma'am,
one.
here all electrons are in same energy state.
No, not necessarily. This is just two electrons in two different spin orbitals, not in same energy state.
To different spin orbit like helium, right?
Like helium, let's say, yeah.
It means I'm interested that same n means that energy is same E orbital energy like helium in that case. That is why
Here,
there.
no, I have not made that assumption. No, I have not made that assumption. The orbital energy can be different as well.
Then why they are indistinguishable?
The why they are indistinguishable.
Yes.
So, by indistinguishable, I mean that if I interchange them, the system's energy will not change. So, if I have, say, electron 1 in energy state E1 and electron 2 in energy state E2, if I interchange electron 1 and 2 and I have electron 2 in energy state E1 and electron 1 in energy state E2, these two systems have the same energy. So there is no, the electrons don't have any identity. The states have an identity.
But the state is represented by the whole theta one, not by H1 and H2.
Exactly.
Then why means H1 sign the expectation value of H1 and expectation value of H2, how that can be same? That is line it confuses me.
Yeah, this is confusing. That is why I let you be confused before I told you that they were equal. The thing is that here you're integrating over the full coordinate space of an electron, uh, and then the identity of electron 1 and 2 does not matter. So the thing is, let's say, if I put an electron in spin orbital 1 or if I put an electron 1 in spin orbital 2, that makes a difference. Like which spin orbitals I am occupying makes a difference. But which particular electron I am using to put in those spin orbitals does not matter.
So, madam, in the
So,
Hamiltonian,
so
did
the
you
if you
write?
have a different occupancy, let's say one electron in chi1 and one in chi3, that is certainly different from one electron in chi1 and one electron in chi2. But there is only one state with one electron in chi1 and one electron in chi2. So putting say electron A in chi1 and electron B in chi2 and putting electron B in chi1 and electron A in chi2, that does not make a difference.
Madam, in the
So
expectation,
here the energy, the state, yeah.
yeah, in the expectation, in the last line, did you write h of small h of one or small h of I? I did not understand that. Last line.
I wrote one. Sorry. Yeah, I wrote one. So by default, the integration coordinate is written as one. Okay,
And
it's written as R1 or
and
H1 or whatever.
the h, it is h1 or hi?
Okay,
I mean,
this is H1. Okay, so I will write it clearly. This is sum over I, chi I, H. I will also write the coordinates of this. So this is x1 and this is H, let's say R1. Okay, and then you have chi I x1. So any one electron, and I'm integrating over the space of that electron. And yeah, just try to think about it. So basically, okay, if we were people, like say you and me, then if I was in chi1 and you were in chi2, that is different from you being in chi1 and me being in chi2. But for electrons, that is not the case. So that is why when the state is the same, so when you are talking about one particular ground state of a system, then interchanging the electrons inside that state don't make a difference to the energy of the state. The state has one constant energy. Okay, can you? Yeah. Okay, it's already 4 o'clock. I'm sorry. Okay, so then maybe this is a good place to stop. Okay, so I will stop here. You think about it, and on Monday we will start here, and we will go on to the other Slater rules then. But this is important to understand. Okay, that which electron I am talking about in my operator. So H basically contains, let's say, a differential operator. So whether I call it differential with respect to quadrant of electron 1 or differential with respect to quadrant of electron 2, that does not matter when my state is the same. Okay. So let me stop here. So can someone stop the recording as well, because I can't do it.